Hi, this is our IC Engine lab presentation by Evelyn, Ryan, and Grace.
The objective for this lab was to determine system parameters and controls for an internal combustion engine that was created by Generative Energy Systems Incorporated. The methods for this lab include, for week 1, calibrating the force transducer to find the torque versus input voltage relationship, characterizing material properties of the engine, which included running the engine without a head or airflow from rest to steady state. It also included determining the flywheel inertia and friction based off of the angular velocity versus angular position of the piston. The 4 strokes of the IC engine, intake, compression, power, and exhaust, will be characterized by running the engine with the head on but no air injection at steady state. The angular velocities and average torques for each of these strokes will be found, which can help to then calculate work. The work is calculated using the flywheel inertia and integrating over the average of the torque versus angular position graphs for each stroke. Looking ahead to week 3, the optimal controls for combustion will be identified. This will be done by running the engine with the head and airflow at steady state and then turning the motor off to verify that the engine is in fact driving the motor and not the other way around. The work kinetic energy model will be updated to account for all relevant variables as well. The system without the engine head attached was used in week 1 to determine certain system parameters, and then in future weeks the system was used with the engine head attached. Here are some important measurements that were taken on the engine in order to perform the proper analysis.
Week 1's experiment is aimed to characterize the material properties of the engine, and the first step is to calibrate the engine torque. This equation is later used to determine the work done by the motor, and the gain and offset torque values can be seen in the legend.
This is the relationship between angular velocity and angular position at 3 different voltages, low, medium, and high, for 2 different engine configurations, one with 1 flywheel and the other with 4 flywheels. This is used to find the steady state value index and will be used later when determining the work of the motor.
Using the calibrated data and the data collected, the average torque versus angular position can be found. Here are the graphs for the lowest voltage for both 1 flywheel and 4 flywheel, and the steady states are shown on both graphs. Same with the medium voltage of 0.6 volts. And finally, the highest voltage of 0.9 volts. This graph shows the relationship between the encoder angle and piston position. They are directly related, and there are diagrams at 0, 90, 180, and 270 degrees to show what the piston crankshaft assembly would look like at each position. This is the work kinetic energy model for this experiment, and quite a few terms are negligible, starting with the kinetic energy at position A, because when it starts it's at rest, therefore the angular velocity is 0. The work to the piston is oscillation due to piston motion, which is negligible due to it being a very small value. Work due to air is negligible because the head is off and there's no airflow, and the work due to discrepancy is 0 because the point of this experiment is to find the model values. Now, using the steady state section of the average torque versus angular position graphs, the work due to friction can be found because it is equal to the work due to the motor. And after the work due to friction is found, it can be used to find the torque due to friction. Then on the same graph from start to steady state, the inertia of the flywheel can be found using the difference between the work due to friction and the work due to the motor, as well as the angular velocity. Using the equations on the previous slide, each of these values can be found. Some things to note are that the inertia of the flywheel on the 4 flywheel system is much greater than the 1 flywheel system, and that for the 1 flywheel system and 4 flywheel system, the inertia stays relatively the same between each of the voltages. Something else to note is that the torque due to friction increases as the voltage increases, therefore making it a Newtonian friction model. Here is a closer look at the torque due to friction versus voltage for both the 1 and 4 flywheel system, and it can be seen that it is a linear increase, therefore confirming that it is Newtonian. Finally, here are the uncertainties for the average torque, the change in angular displacement, and the work due to the motor for the 1 flywheel and 4 flywheel systems.
The process from week 1 to week 2 remains relatively the same, at least in the beginning stages. Since the head is now on the IC engine, we need to recalibrate the force transducer so the torque data is accurate. The gain and torque offset values are similar but not the same from week 1. The main goal of week 2 is to find the angular velocities and average torques for each of the 4 representative strokes. When the IC engine is running at steady state, we can create plots for each of these 4 strokes on an IC engine. These strokes are intake, compression, power, and exhaust. For the intake and exhaust strokes, represented by the blue and black data points respectively, these valves are open, which allows the pressure to remain at the atmospheric pressure. This is shown by the angular velocities and torque values being relatively the same between said strokes. The angular velocities hover around 37 radians per second, and then the torque values range from negative 1.5 to 0.5 newton meters when the input voltage is 0.3 volts. The compressor stroke works by moving the piston from bottom dead center to top dead center while the valves are closed. This causes a large dip in the angular velocity, as shown with the red data points, and then a large increase in the torque, shown by the red data points in the torque plot. This is due to a very large increase in the pressure. Now the power stroke works in the opposite direction by moving the piston from top dead center to bottom dead center. This is shown by the opposite reaction with an increase in angular velocity and a large decrease in the torque. As we have learned from week 1, the input voltage has a meaningful impact on the behavior of the IC engine. While one would assume both the angular velocity and average torque to increase as the input voltage increases, this is not the case. As previously shown, the steady-state angular velocity will increase as the input voltage increases. This can be seen by comparing the 0.3 volt data to 0.6 volt data. The 0.3 volt peak is at 37 radians per second, while the new peak reaches about 47 radians per second. As for the average torque of the strokes, there is a decrease in the overall torque in the system as the input voltage increases. This can be explained by the Newtonian friction model. As the input voltage increases, so does the friction acting on the system. An increase in the input voltage from 0.3 to 0.6 volts is what leads to the overall voltage to decrease from negative 3.5 newton meters to negative 2.75 newton meters. Another example of this trend is observing the new angular velocity and average torque data when increasing from the previous 0.3 or 0.6 volt data to 0.9 volt data. The average velocity peaks for the previous voltages are no longer on the plots, as the new peak when given a 0.9 volt input is now 72 radians per second. The same can be said about the average torque data. The increase in torque due to friction now decreases the overall torque to about negative 2.5 newton meters.
Another variable that can change the behavior of the 4 strokes is the mass of the flywheel. As seen from week 1, the moment of inertia using 1 fly mass when compared to 4 fly masses is much less. This leads to some interesting observations. When observing the effects of the inertia on the angular velocity of the representative strokes, the peak for the 1 fly data is much larger than the 4 fly data. The increase in inertia allows the flywheel to be stopped more easily as the flywheel moves during the strokes. When running the engine, the rotation of the flywheel can be seen as jerky when running with 4 fly masses. As for the average torque data, the same observation can be seen when comparing 1 fly mass data with 4 fly masses. Since the flywheel with 1 fly mass can accelerate and decelerate easier, the torque can increase and decrease at the same rate. This allows the motor to reach its maximum torque at each stroke before moving on to the next stroke in the cycle. As seen in the plots, there is about 2 times difference between the maximum average torque between the 1 fly mass and the 4 fly masses data.
Now that the head is on the engine, the work energy model needs to be updated. The work from the piston can no longer be assumed to be negligible due to the engine running through cycles at different pressures. This also introduces a work discrepancy. In an ideal world, there will be no pressure loss between the strokes due to air loss or a bad seal. However, the work discrepancy shows that loss in work due to said difference.
Looking ahead for week 3, the system will of course be calibrated first. Then, to simulate combustion, the engine head will stay on and air will be injected into the system. In this week, the optimal controls for combustion will be identified. In order to maximize work output, the start and end injection angles will be determined as well as the minimum voltage that can be reached without stalling. The voltage for which the engine drives the motor will be found by running the engine and then turning the motor off to prove that the engine is in fact driving the motor. In week 3, the work kinetic energy model will be updated as well to account for the injection of air. The additional terms include the work from air and the work from the discrepancy. The work from the discrepancy is a term that quantifies the difference between the experimentally determined work from air and the theoretically determined work from air. This helps determine the quality of the model to predict experimental behavior. Once the data is collected and analyzed for week 3, the specified uncertainties will also be calculated for the system.